Now moving on to sound, which I think is probably like the simplest thing, most reasonable thing from this lecture. Because what is sound, right? Sound's a wave. I'm sure many of you knew that. Sound's a wave created due to the vibration of an object causing ripples through space and like kind of being passed on through. That's actually, I would say, not exactly accurate. It's not through space. It's through molecules in space. So I would say through molecules in space, because it can move through most mediums like air, water, and solids, because it transfers vibrational motion from one particle to the next particle in the medium. Without a medium, like for example in space, in outer space, it can't travel because there's nothing to pass it on to, right? So for example, if my throat was to create a vibration and is going to come out of my mouth, well, if right now it's going through the air, right? So it's going from my throat molecules to the air molecule and the next air molecule and so on and so forth, through each air molecule. If we were in space, no air molecules, it would reach the last throat molecule and then it would go nowhere, right? Because it can't go through nothing. It has to go through some kind of molecule. It has to be passed down from molecule to molecule. Kind of like a chain reaction. Like if you were to create like a wave in a stadium, like the rising wave, like where they go like this. If there's nobody there, you can't make a wave because there's nobody there. You can't pass it on to anybody, right? Same thing for sound. The standard unit of sound is decibels. Generally, it ranges from about 20, which is like a whisper, clock ticking. It does actually start at 0, but from 0 to 20 is like so quiet you don't really, like nothing's really between 0 and like 20. 20 is kind of like the lowest that we really hear, and this will come up a little bit later, but this relates to intensity, and decibel measures sound volume, right? How loud something is. Okay. So it's again range from 20, which is a whisper or clock ticking, to about 150, which is usually like a gunshot or a jet engine or something really loud, right? If you go above like 80, 90, I think you start hurting your ears, so it's really not good to be around anything that's more than 80 or 90. Okay. Intensity. So decibel is not really a scientific measurement. It's more like a human measurement. Like we use it because it's easy. Kind of like how like Fahrenheit or like pounds are not really scientific measurements. They're measurements that we use because they're easy. The more accurate term is intensity of the sound wave, and that's measured in watts per meter squared. We can very easily convert intensity to decibels, and it uses the equation L equals 10 log intensity over I0. L is decibels, I is intensity, and I0 is the baseline intensity. We arbitrarily picked this baseline. It doesn't have to be that, but science, or like somebody like made the rule that that is the baseline, and we chose that baseline as to be 0 decibels. So for example, if the intensity of the sound is the same as the baseline we picked, we consider that sound to be 0 decibels. And all other sounds we compare to that baseline. So all other sounds are relative to that arbitrary 0 that we picked. Okay. The arbitrary 0, it's actually equal to 10 to the negative 12 watt per meter squared, right? Again, being able to do basic log math is very important for the MCAT for a variety of topics, not just this, but a lot of acid and base stuff with pKa's, and Ka is very important, pH. I would say it's make sure you're comfortable with doing logarithmic math in your head or on paper. I'll give you a very quick example, but there's many other lectures that I've already went over this, but I'll just go through it again. So for example, if you were to be given, so we know that I0 is 10 to the negative 12. if they gave you a sound, for example, somebody yells really loud next to you, and you find that to be have an intensity of 10 to the negative 6th, right? You want to convert this intensity 10 to the negative 6th into decibels. How would you do that? Well, you do 10 to the negative 6th over divided by 10 to the negative 12, which is this, right? And right, when you do that, you know that this is 6 powers greater. For this one, it's actually easy. You don't even have to really do that much. You know it's 6 powers greater, right? Because 6 is 6 more than 12, or 6 less than 12, but like negative 6 is 6 more than negative 12. I should say, sorry. 6 is 6 more, negative 6 is 6 more than negative 12. So log is just, you can take the power, so you know it's 6 times more. So if you do the log, it'll cancel, and you do negative 6 minus negative 12, and you end up getting 6. So this log is equal to 6, right? And then you multiply by 10, and you get 60, and that's decibel of 60. Right? Does that make sense? And just again, if you remember what a log is the inverse. I always say this: log is the inverse of 10 to the power, right? Just like multiplication is the opposite of division. So if you multiply something by 5, and then you want to get rid of that, you would just divide it by 5, right? So if you had 5x, you wanted to isolate the x, you would divide, right? Because instead of multiplication, which is happening here, you would use division, which is the opposite, and then you just get x. Same thing here. If you had 10 to the x and you wanted to isolate x, you do the opposite of 10 to the power, which is log, right? And then the log cancels out to 10 to the power, and you're just left with x. Just like with multiplication, you would divide. Okay, so essentially, if you have 10 to the negative 6 over 10 to the negative 12, then you have the log of that. When you do log to that, you can cancel out this, cancel out this, cancel out this. You're just left with negative 6. And remember, log is actually, for division, log is this. So what this means is this is the same thing as this. This might actually be more helpful if you want to understand it, whereas this is more helpful to do this form at the bottom. This and this are the same thing. This notation and this notation are the same thing. So again, cancel, 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 cancel. Because these are the opposites. These are the opposites. You're just left with negative 6 minus negative 12. And then that's 6, right? But when you have it in this form, it's actually easier to do because you already can see 6 is 6 more. So you can just do 6 and then times 10. Hopefully that wasn't too confusing, more confusing. Yeah. But again, if you are having trouble with logarithmic math, it is going to come up on the MCAT. I'm very confident that you'll see at least a couple of questions that do require you to know logs. So get comfortable with it. Okay, next, moving on to other aspects of sound waves. As all other waves do, like light and everything else, sound has a frequency. Due to it being such a commonly observed wave by humans, we have given the frequency of sound waves a special name called pitch. We can estimate the frequency of the wave just by observing it, which is hearing it. For most of the waves, at least, for most sound waves, at least, there's some we can't differentiate because our ears aren't built that way. But yeah, high frequency is a high pitch. Low frequency is a low pitch, right? There are many musical applications to knowing and manipulating pitches and frequencies. For example, creating 2 waves simultaneously in a 2-to-1 frequency ratio, like for example, 512 hertz and 256 hertz creates a pleasant sound. That ratio is called an octave, and that's used very commonly in music. So if you want to do something like in an octave higher, you just do this 2-to-1 ratio. People who are more musically inclined than me will probably understand this very well, but I don't think it's too complicated. Volume is intensity, like we just talked about, decibels. Frequency is high pitch, low pitch. High pitch, you know what high pitch sounds like, you know what low pitch sounds like, right? That's frequency, and wavelength and frequency are tied, remember. So intensity is the loudness, pitch is like the frequency for sound waves. Next, let's talk about Doppler effect and the shock waves. Previously, we talked about Doppler effect in great detail, along with all the math and everything for it. However, when we discussed previously, we only ever gave cases where the moving object is moving at a velocity lower than the speed of sound, right? And that was a big contingent, like the Doppler effect's formula is very contingent on that fact, because it would kind of get much more complicated and way more difficult if you didn't. If you had an object that was moving faster than the speed of sound, but you know that things do move faster than the speed of sound. There are many projectiles and even objects such as like jets that we have now, which can move beyond the speed of sound. These create a very difficult sound interaction through something called a shock wave. It's literally like kind of like a boom or like an explosion, because of the pressure difference that it creates in the air. Well, we're not going to cover it in detail due to its complexity. Know that this is a phenomenon which kind of things move faster than the speed of sound. You can't really use the Doppler effect. You can kind of, but the math is much more complicated, and it creates a big pressure difference, which creates a sonic boom in the air. Next, ultrasound. As mentioned, waves come in different frequencies. Humans can hear from about 20 hertz to about 20,000 hertz, 20 kilohertz. That's the K and the hertz stands for. It's 20,000 or 20 kilo. So anything above 20 kilohertz is not detectable by human ears, but there are other animals like bats which can create and detect these vibrations, and they use them for navigation purposes, echolocation. Based off this, humans have developed devices which can create ultrasound waves from about 20 kilohertz to about 15 megahertz, which is in the millions, to use for medical purposes. Using the known speed of the sound wave and measuring the time it takes to create the created wave to bounce back to the machine, we can determine the type and location of certain tissue. Essentially, here's a machine. Here's a guy. Say you're doing ultrasound. This is some guy's stomach, for example. You're doing an ultrasound of the abdomen. The machine will go through a echo phase where it'll create a sound wave which goes in, like out, out. It hits something in his stomach, hits like the tissue, then it bounces back to the machine. As soon as the machine releases the sound, it goes into like a listening phase where it listens for the sound back. Once it hears the sound back, it can then measure, okay, the speed of the sound wave was this speed. If it had to move, and the distance between me and the person is this many meters, that means the sound must have traveled this long before being bounced back and coming back to me. So that means there's some solid object this many meters or this many centimeters or this many millimeters away from me, right? And then it'll do it again and again and again and again and again, and just from a variety of different angles and different ways. And then using digital manipulation or kind of like digital algorithms, it'll combine all of those like tiny snapshots that it got into a complete picture. And from there, it'll be able to tell, it'll basically be able to make a 3D model of your abdomen because it knows the exact location of every essentially spot where it is, right? Okay, that makes sense because it knows like there's something solid right here and right here, but there's nothing solid right here. So that means this is an empty space. Then I'll go from a different angle and say, okay, there's something solid here, 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 not here. So that means it ends. Then it'll go from a different angle, solid, and then like that. And it'll say like this is your kidney or something, or like your liver. right? And this is what the shape of your liver is, because there's no solid object here or under or to the right or to the left, but there are solid objects all the way over here, which we detected by sound waves. Okay, hopefully that makes sense. Essentially like echolocation. And we use a lot of digital manipulation. Okay. I think if you really need to know more, at least for the purpose of the MCAT, if you need to know more about ultrasounds, I'll give you a passage where they'll talk about what ultrasound is and how it works and everything like that. This is just like a very basic definition. I don't think they'll ask you in depth anything beyond this unless they give you a passage in which they tell you more about it, which is actually kind of common. They do give a lot of ultrasound passages, so it's definitely not something that's uncommon. If you're also interested in this on your own, again, I encourage you to do more research on this on your own. But I think this is like a basic understanding of sound and sound waves and how ultrasound works to be able to understand if you do your own research. Okay.